In this video, we are going to learn about boundary layer formation while fluid is flowing over the plate. So let's start. So the first point is what is the boundary layer and the boundary layer theory. So second point will be definition of laminar and turbulent boundary layer. Third point will be laminar sublayer, and fourth different types of thickness, what we are going to discuss subsequently. So first will be boundary layer thickness, definition of boundary layer thickness, then displacement thickness, then momentum thickness, and then energy thickness. So let us start one by one. So first point is what is boundary layer and the boundary layer theory. To understand this concept, consider the solid wall, and when a real fluid flow past the solid body and solid wall, the fluid particles adheres to the boundary and the condition of no slips occurs. See, when a real fluid means the fluid which has got the viscosity and the density. So when it's flow over the plate, the very first layer adjacent to the boundary will adhere, means will stick to the boundary, and there will be the condition of no slip. This means that when fluid is flowing over the boundary, the velocity of fluid close to the boundary will be same as that of a boundary. So if the boundary is stationary, the very first layer of the fluid will also be stationary, as you can see here. The first layer has zero velocity. When we go away from the boundary layer in the direction of y, fluid layer has got the velocity increasing in the direction of y. You can see here the second layer has more velocity than the first, and third has got the more velocity than this second layer. Similarly, all the layers adjacent to this third layer on the upper side has got the more velocity until the velocity is equal to the free stream velocity, that is equal to the u. So the velocity at this boundary layer is 0, and it is going to increase towards y direction. Here you can see, and this variation in the velocity is nothing but the velocity gradient, which is denoted by du by dy. So the velocity of fluid increases from 0 velocity on the stationary boundary to free stream velocity u of the fluid in the direction of normal to the boundary. This variation of the velocity from 0 to free stream velocity in the direction normal to the boundary take place in the very narrow region of the boundary. See, entire things is taking place, entire variation of the velocity is taking place in the very narrow region of the boundary, and this narrow region is called boundary layer. Got it? And this boundary layer we are going to study in this video. And the theory what we are going to utilize to study the boundary layer, that is nothing but the boundary layer theory. So according to this boundary layer theory, the flow of fluid in the neighborhood to the solid boundary is divided into two regions. The very first region is the boundary layer in the immediate neighborhood to solid boundary, where the variation of velocity from 0 to the solid boundary, 0 at the solid boundary to the free stream velocity takes place in the y direction. So in this region, as we already seen that velocity gradient du exists, du by dy exists, and hence the fluid exerts the shear stress. Here you can see the two arrow indicates that the two layers are sliding on each other, and thus they exert a shear stress on each other in the direction of the flow. And this shear stress is given by will be given by the Newton's law of viscosity, that is nothing but u into du by dy. And the second region will be turbulent layer. Second layer of the boundary layer will be equal to the second layer will be outside the boundary layer, and that layer has got the velocity equal to the u. As there is no variation in that region, the velocity gradient will be zero. As a result of that, there will be no shear trace. So whatever the flow above this region, there will no viscosity. There will be viscosity, but there will be not the velocity gradient, and there will not be any shear stress. This entire boundary layer is divided into number of different layers depending upon the types of phenomena that fluid is following during its flow. So the very first layer is the laminar boundary layer. So let us consider the fluid having the free stream velocity u, as you can see in this diagram, and the velocity of the fluid on the surface of the plate should be equal to the velocity of plate, as we already seen. And we also seen that the plate is stationary, and hence the velocity of the fluid on the surface of the plate is zero. But at a distance away from the plate, the fluid is having the certain velocity. Thus the velocity gradient is set up in the fluid near the surface of plate. These velocity gradients develop a shear resistance which pulls back the fluid, and thus the fluid with the uniform free stream velocity is further pulled back in the narrow region of the solid surface of the plate, and the boundary layer region begins at the very sharp leading edge. At the subsequent point downstream the leading edge, the boundary layer region increases because the pulled fluid is further pulled back, and this is also referred to as a growth of boundary layer. Near the leading edge of the surface plate, where the thickness is small, the flow in the boundary layer is laminar, though the main flow is turbulent. This layer of the fluid is said to be laminar boundary layer. And we can see it is shown by the AE. The length of the plate from the leading edge up to which a boundary layer exists is called the laminar zone. This shown by the distance AB. The distance B from the leading edge is obtained from the Reynolds number, which is equal to 5 into 10 raised to 5 for the plate. Because up to this Reynolds number, the boundary layer is laminar. The Reynolds number is given by u into x by nu is used to find this AB distance. Here in this equation, if we put all these values of u, nu, we are going to get the value of x, and the value of x is nothing but the distance of laminar zone. So this is overall about the laminar boundary layer. If the length of plate is more than the distance x, what we seen to calculate just now, the thickness of the boundary layer will goes on increasing in the downstream direction. Then the laminar boundary layers become unstable. Here you can see the boundary layers is becoming the unstable here in this region. So because of this unstable boundary layer, motion of fluid within it is disturbed, it's irregular, and boundary layer changes from the laminar to the turbulent. Here you can see all the fluid particles are moving in randomly and in disturbed manner. So here you can say that the laminar boundary layer is changing from laminar to turbulent, and this happens in a very narrow zone, and this zone is called a transition zone. Further, the downstream of this transition zone, the boundary layer is turbulent and continues to grow, and this layer of the boundary is called the turbulent boundary layers, which you can see here. from F up to this G. Okay, and this we call it as a turbulent boundary layer. So let us see what is a laminar sublayer. Similarly, in the turbulent zone, there is one very thin layer of this fluid in which the velocity distribution normally would be parabolic, but since the thickness of this laminar sublayer zone is very small, so that velocity variation will be linear in this. Okay, I will repeat again. In this turbulent boundary layer zone, adjacent to this solid surface, the velocity variation is influenced only by the viscous effect. Though the velocity distribution would be parabolic curve in the laminar sublayer zone, but in the view of very small thickness, we can reasonably assume that velocity variation is linear, so velocity gradient can be considered as a constant. Therefore, shear trace in this zone would be constant and there will be no shear trace. The shear trace will be 0. So we can see that by the Newton's law of viscosity, we got this equation for the laminar sublayer. It's all about the laminar sublayer. I hope it's clear to you. Now, if we combine the boundary layer flow in the one diagram, it will look like this, as you can see in this diagram. Here first will be laminar zone, followed by the transition zone and then turbulent zone. The every flow which flows from pipe or over the smooth plate or over any section that follows this phenomena when it's flow over any surface. Understood? Okay. So very first definition in this we are going to see is about boundary layer thickness. So up to what thickness this boundary layer will exist in the flow. So the distance from the boundary of the solid body measured in the y direction to the point where the velocity of the fluid is approximately equal to the 0.99 times the free velocity u of the fluid. You can imagine this statement in your mind and it will be very clearly understood to you by yourself. So this boundary layer thickness is denoted by delta. Now you imagine there is one solid wall. The very first layer of this fluid near to the solid wall will be stationary because of the solid wall is stationary, and the second layer has got the same velocity, and third layer is getting more velocity than the second one. So likewise every layer towards the y direction is getting more and more velocity. So there will be increase of velocity in the y direction, and the point will come when this fluid layer will be equal to 0.992 free stream velocity, and this distance is nothing but the boundary layer thickness. Okay, I think it's clear to you. Now we are going to see the terms called the displacement thickness. This is a part of this boundary layer theory. So the definition of displacement thickness is that the distance perpendicular to the boundary by which the free stream is displaced due to the formation of boundary layer, and it is denoted by delta star. So you can imagine that it is defined as the distance measured perpendicular to the boundary of the solid body by which boundary should be displaced to compensate for the reduction in the flow rate on the account of boundary layer formation. So whatever the loss of flow rate due to the boundary layer formation, that will be filled up with this displacement thickness if the boundary layer is displaced by that much amount. Okay, understood? Now let us see the expression for displacement thickness. Consider the flow of fluid having the free stream velocity equal to u over the thin smooth plate as shown in the figure. At a distance x from the leading edge, consider the section 1-1. The velocity of fluid at the B is 0 and the C, which is lie on the boundary layer, the velocity at the C is u. The velocities varies from 0 at B to u at C, where the BC is equal to the thickness of boundary layer. And let us consider that the dy is the thickness of the elemental strip at a distance y from the solid plates, having the u as a velocity of the fluid, and this entire fluid has got the width of b. So now see that how we are going to derive the expression for displacement thickness. The area of this elemental strip is nothing but the width into the thickness. The width is b and into the thickness is dy. So area of the elemental strip is equal to the dA is equal b into dy. Now if you see this diagram, in this the mass of fluid per second flowing through this elemental strip dy, the mass of fluid flowing through it will be equal to density into u into dA. That is, we can see this equation as that of the continuity equation. The continuity equation which is based on the law of conservation of mass. Okay, so that mass will be equal to the rho into u into dA. Here rho is a density, u is a velocity, and dA is area. So area is nothing but the width into thickness, and thickness is nothing but b into dy. And if you are given this equation as a number 1, then if you assume that if there had been no plate, then the fluid would have been flowing with the constant velocity equal to the free stream velocity at the section 1-1, then the mass of fluid per second flowing through the elemental strip would have been. Did you understand this statement? If in the flow, if there is no plate, then the flow of fluid will be equal to the free stream velocity. There will not be any velocity gradient at all, and there will not be a shear stress in the fluid flowing. So if we consider the situation, then the mass of fluid flowing through that entire section will be rho into velocity into area, but here the velocity will be equal to the free stream velocity because we assume that. Okay, then further we will solve this. Before solving this, we will give this equation as a number 2. Hence, so there will be the reduction in the mass of the fluid per second flowing through the elemental strip, and there that we are going to get from minusing mass of the fluid per second given by the equation number 2 by equation number 1. So here you can see that rho u b dy minus rho u b dy, this is with plate and without plate, the flow of fluid. So we are taking these terms outside of the bracket and solving this equation. So this reduction in the mass is for very small elemental strip. So in order to get the reduction of the mass for throughout the section, we need to integrate this equation between the limit that is 0 to delta. So upon integration, we are going to get this equation. So for integration, this constant terms will come out of integration, and the integration of 0 to delta of u minus u bracket dy, and this equation will give number 3, and this equation we are going to use in further analysis. Now let this plate This solid plate is displaced by the distance nothing but delta star, and velocity of flow for the distance delta star is equal to the free stream velocity. Okay, the loss of the mass of the fluid per second flowing through the distance delta star will be equal to the density into velocity, free stream velocity into delta star into B, and these two terms is nothing but the area. So the loss of fluid flowing through the elemental strip or for the entire section, what we got after integration, will be equal to the mass of the fluid flowing when it boundary is displaced by the delta star. That will be equal, that we get it from definition itself. The definition of displacement thickness says that the loss, for compensating the loss of fluid flowing through the boundary layer, we need to displace this boundary layer by delta t, delta star. So using that statement, we are equating the both the equation, and we are going to get is rho into b integration 0 to delta bracket u minus u bracket close dy is equal rho into u into delta star into b. So these both the terms, this one and this one and this is going to cancel, and what we are going to get is integration 0 to delta under bracket u minus u bracket close dy is equal u into delta star. Delta star is equal 1 minus u into integration between 0 to delta under bracket u minus u delta dy. Upon solving this 1 by u will multiply inside the integration, and it will become delta star is equal integration between 0 to delta under bracket u minus u dy by u. So this u will divide to this u and it will get cancelled and it will become equal to 1, and these terms will remain as it is. So finally the displacement thickness for the boundary layer we are going to get from integration 0 to delta under bracket 1 minus u by u bracket close dy. So that was about the displacement thickness. And the second terms we are going to calculate is the momentum. When there is a momentum, when there is a formation of the boundary layer, there will be the change in the momentum of the fluid near the boundary layer, and that change in the momentum of the boundary layer, to calculate that change we have the momentum thickness. So it is defined as the distance measured perpendicular to the boundary of the solid body by which boundary should be displaced to the compensate for the reduction in the moment of the flowing fluid on the account of the boundary layer formation. Okay, here we are creating the another imaginary thickness that will displace the boundary to compensate the reduction of the momentum. Okay, so this is denoted by the theta. And again making the same assumption what we have seen earlier, the flow of fluid, free stream fluid, is flowing over the thin plate, and we are considering the very small elemental strip of the thickness dy at a distance y from the solid plate, and the area of this small strip plate, as already we have seen, is b into dy. So the momentum of the fluid of the mass flowing through the elemental strip we need to calculate. So momentum of the fluid is equal mass into the velocity, that is from the momentum equations. Okay, so the mass is nothing but rho into u into b into dy. This b into dy is the area, this is the velocity, and this is a density into the velocity is equal to the u. So now we need to calculate the momentum of the fluid in the absence of the boundary layer is equal rho into b into d into dy. If there is no boundary layer, the velocity equal to the free stream velocity, that is a big U. So the loss of momentum through this elemental strip, we are going to get it from minusing this equation from this equation. So the momentum we are going to get is rho into u into b under bracket u minus u into dy. So total loss of momentum per second through the whole BC section is we are going to get by integration between limit 0 to delta. Delta is nothing but the boundary layer thickness. Okay, so the total loss of momentum is equal to integration between limit 0 to delta rho into u into b under bracket u minus u dy, and that is the total loss of momentum due to the formation of the boundary layer. So now let us consider that theta is the distance by which a plate is displaced when the fluid is flowing with a constant velocity u. Okay, therefore the loss of momentum of the fluid flowing through the distance theta with the velocity u will be equal to the mass of the fluid through the theta into the velocity. So mass of the fluid flowing through the theta will be equal to the density into area into velocity into the velocity. So this velocity will be equal to, this momentum loss will be equal to the rho into theta into b into u into u. Theta into b is nothing but the area. So upon solving this, u will multiply inside this and it will become a density into theta into b into u square, and this equation consider as the number 5. And this both equation, this one and the previous one, we are going to equate, and we are going to get is a rho into theta into b into u square is equal integration from 0 to delta rho u b into u minus u into dy. Now we are taking this rho into b because as a constant term it will come out of the integration, and this rho b and this rho b is getting cancelled, and upon cancelling that we are going to get is theta into u square is equal integration between limit 0 to delta u into u minus u into dy. Now this u square will will divide this side, and it's going to be theta is equal 1 minus u square integration between limit, and these terms will come as it is. Now this whole derivation you can see here in the one glance, and this u is going to multiply in this inside, and it will be become theta is equal 0 to delta u into u minus u into dy by u square. So upon solving this, we are going to get is this equation. This u will divide this one, this u also will divide this one. So the common terms will come out of this, and we are going to get is theta is equal integration between 0 to delta u into u minus 1 minus u by u bracket closed dy, and this is nothing but the momentum thickness. So to calculate the momentum thickness we need to use this equation. Okay, so last in this video the last term we are going to talk about is energy thickness. So whenever there is a formation of the boundary layer, there will be loss of energy. So in order to compensate that loss of energy, we need to displace the solid plate by a certain distance, and that distance is nothing but the energy thickness. Okay, so definition is also saying the same thing. So we can see that here the distance measured perpendicular to the boundary of this solid layer by which boundary should be displaced to compensate for reduction in the kinetic energy of the fluid on the account of boundary layer formation, and this is denoted by the delta star star double star. Okay, so in order to derive the equation for the energy thickness, again we need to consider the same diagram. Assume that the fluid having the free stream velocity v in the direction of left to right over the small plate and at a distance x from the, there is one section having the velocity at the boundary is equal to 0 and on the boundary is equal to free stream velocity, and there will be one elemental strip of the thickness dy at a distance y from the solid plates, and through the elemental strip there will be velocity of the fluid equal to the u, and the solid plate has got the width of b and the area of this elemental strip will be equal to the b into dy. So as we know that the kinetic energy is calculated from this formula, that is equal to 1 by 2 mass into the velocity square. So we'll substitute the value of mass and velocity into this equation. Upon substituting this value, we are going to get is the kinetic energy is equal to 1 by 2 into rho into u into b into dy into u square. So kinetic energy of the fluid in the absence of the boundary layer will be equal to the mass into the free stream velocity, and we are going to substitute this value in this, and upon substituting we are going to get this equation. So because of this formation of the boundary layer, the loss of kinetic energy through this elemental strip will be equal to the this equation minus this equation. So upon substituting these values, we are going to get is loss of kinetic energy equal to 1 by 2 into rho into u into b under bracket u square minus u square into dy. So the loss of kinetic energy that is calculated for the small elemental strip. In order to calculate the loss of kinetic energy for whole thickness BC, we are going to get it from integration. So we will integrate this whole equation. Upon integration, we are going to get is 1 by 2 rho into b integration 0 to delta u into u square minus u square dy. So this is constant terms will come out of this integration, and we'll name it as a number 8. So now consider a delta star star is the distance by which the plate is displaced to compensate for the reduction in kinetic energy. Okay. So loss of kinetic energy through delta star star of the fluid flowing with the velocity u. So that is we are going to calculate from this equation, that is nothing but 1 by 2 mass into velocity square. Upon substituting the values of mass and the velocity in this equation, we are going to get is 1 by 2 under bracket density into width into thickness by which plate is displaced into u into v square. So this u square will multiply inside this, and equation will become 1 by 2 rho into b into delta double star into u cube, and give it as a number 9. And this both the equation will substitute as the statement of this energy thickness say in the definition. So upon equating both the equation, we are going to get is delta double star is equal 1 by q integration between the limit 0 to delta u under bracket u square minus u square by dy. So this u 1 by u cube will multiply inside the integration, and it will become as a delta star star, the integration from 0 to delta u by u under square bracket 1 minus u square by u square under bracket dy, and this is called energy thickness. So from this equation we can calculate the energy thickness. The energy thickness is nothing but the distance by which the plate should be or the boundary should be displaced to compensate for the energy loss. Okay, I hope it is clear to you. All the things are clear to you. What is boundary layer, what is boundary layer thickness, laminar sublayer, laminar zone, turbulent zone, everything, and this the thicknesses, various thickness for the compensation of the various parameters. I think it's clear. If it's clear to you, it's understandable to you, then please subscribe to my channel, and thanks for the watching the video.